There is a deep and a profound comfort to be found in a story that makes sense. In our own lives and in our science, we have a fundamental need to see the world as a coherent and a logical place. For the last few decades, the science of cosmology has given us just such a story. It is a grand, a beautiful, and an incredibly successful narrative of our universe, from its first fiery moments in the Big Bang to the slow and patient evolution of the great galaxies that we see today. This story, our standard model of cosmology, has been a triumphant achievement of the human mind. It has been tested and confirmed and refined by thousands of observations, and it has given us a sense of a deep and a satisfying understanding of our own cosmic home. But in the quiet halls of astronomy, in the faint and distant light from the edge of the universe, a beautiful and a troubling mystery has emerged. A single, stubborn, and an undeniable clue that suggests our great and comfortable story of the universe might be wrong. It is a mystery that has been given a simple and a gentle name. It is known as the Hubble Tension, and it is, without exaggeration, the single greatest and most exciting puzzle in all of modern cosmology. The story of this tension is a quiet and a careful detective story. It is the story of two completely independent and incredibly precise methods that scientists use to measure the single most important number in the entire universe, the rate at which our cosmos is expanding. And the great and beautiful problem is that these two gold standard methods, when we perform them with our most powerful and our most precise instruments, are giving us two different and incompatible answers. It is as if we have taken a single precious object and we have measured its length with two different and perfectly calibrated rulers. And one ruler is telling us that the object is 10 inches long, and the other is telling us that it is 11. Both rulers are of the highest possible quality. Both measurements have been checked and rechecked and confirmed, and yet they disagree. And this quiet and persistent and now statistically undeniable disagreement is a whisper from the cosmos itself. It is a gentle and an insistent and a beautiful message that there is a deep and a profound and a thrilling new chapter of our universe that we have not yet even begun to understand. Before we begin our calm and patient journey into the heart of this cosmic crisis, I would love to know from which part of our own quietly expanding corner of the universe you are joining us tonight. Please write your city or your country in the comments below. It is a beautiful way to feel our shared connection as we prepare to explore the very fabric of our reality. And if you enjoy these deep and educational journeys into the greatest mysteries of our cosmos, please consider subscribing to the channel. Your support is the quiet energy that allows these explorations to continue, always calmly, always at the pace of the universe. Our journey tonight will be a calm and a careful one. We will not be rushing to a simple or sensationalist answer. Instead, we will together become cosmic detectives. We will first travel back in time to the early 20th century to witness the historic and the revolutionary discovery that our universe is, in fact, expanding at all. We will then explore the two great and different methods that we now use to measure this expansion. The first is a journey to the very beginning of time itself, to the faint and the ancient and the beautiful afterglow of the Big Bang, the cosmic microwave background. We will see how, from this baby picture of the universe, we can use our standard model of cosmology to predict how fast the universe should be expanding today. And then we will take a second journey, this time through our own modern and local universe. We will climb the great cosmic distance ladder, using special pulsating stars and spectacular exploding supernovae as our rungs, to directly measure how fast the universe is expanding today. And then we will stand in the quiet and the beautiful space of the disagreement, the great Hubble tension itself. We will explore the possibility that our measurements are wrong. And finally, and most excitingly, we will explore the thrilling and the revolutionary possibility that our measurements are right, and that the beautiful and the successful and the comfortable story that we have been telling ourselves about our universe for the last 50 years is, in some deep and fundamental way, incomplete. To truly understand the beautiful and profound crisis of the Hubble tension, we must first journey back in time to a little over a century ago, to a moment when our understanding of the universe was on the cusp of its greatest and most violent revolution. We must return to a time when the very idea of an expanding universe was not just unknown, it was considered a physical and a philosophical impossibility. For most of human history, and for the great minds of science, including Albert Einstein himself, the universe was assumed to be a static, an eternal, and an unchanging place. The great starry river of our own Milky Way galaxy was thought to be the entirety of existence, a single, vast, and solitary island of stars in an infinite and otherwise completely empty ocean of space. This was the comfortable, the logical, and the deeply ingrained picture of our cosmos. It was a picture that was about to be completely and utterly shattered. The first, quiet, and almost accidental clue that something was profoundly wrong with this static picture of the universe came from the patient and meticulous work of an American astronomer named Vesto Slipher. Working in the early 1900s at the Lowell Observatory in Arizona, Slipher was not trying to discover the fate of the universe. He was trying to solve a much more local and a much more debated question. The skies, as seen through the powerful telescopes of the time, were filled with faint, fuzzy, and beautiful smudges of light, objects that were known as spiral nebulae. And the great astronomical debate of the era was a simple one. What were they? Were they, as most astronomers believed, clouds of gas and dust that existed within our own Milky Way, perhaps the birthplaces of new solar systems? Or were they, as a small and a more radical group of thinkers proposed, distant and colossal island universes, entire galaxies in their own right, located far, far beyond the borders of our own? To help solve this puzzle, Vesto Slipher spent years, from 1912 to the mid-1920s, doing something that no one had ever done before with such precision. He used the science of spectroscopy to carefully measure the light from these spiral nebulae. He was looking for the Doppler shift in their light, the telltale sign that would reveal their motion. If the light from a nebula was shifted towards the blue end of the spectrum, it meant it was moving towards us, and if it was shifted towards the red end, it meant it was moving away from us. Slipher, assuming that these nebulae were objects inside our own Milky Way, expected to find a random and a roughly even mix of red shifts and blue shifts, as these objects should be swirling about the galaxy in all different directions, just as the stars do. But what he found was astonishing and completely inexplicable. Of the more than 40 spiral nebulae that he measured, almost all of them were dramatically redshifted. They were all, with only a few nearby exceptions, moving away from us. And they were moving away at incredible and previously unheard of speeds, some at more than 1,000,000 miles per hour. It was a profound and a deeply unsettling mystery. The universe, it seemed, was not a static and a random place. It seems to have a strange and a powerful and a universal outward motion, but no one knew why. The second and the decisive piece of the puzzle was put in place by the great astronomer Edwin Hubble. Working in the 1920s with the new and then the most powerful telescope in the world, the 100-inch Hooker telescope on Mount Wilson in California, Hubble set out to solve the great debate once and for all. He wanted to measure the true distance to these nebulae. To do this, he used a new and a powerful cosmic yardstick, a special and a wonderful kind of star known as a Cepheid variable. Discovered by the brilliant astronomer Henrietta Leavitt, these stars have a miraculous property. They pulsate, growing brighter and then dimmer, with a rhythm that is directly and precisely related to their true intrinsic brightness. By measuring how fast a Cepheid star is pulsing, you can know exactly how bright it truly is. And by comparing its true brightness to how dim it appears in the sky, you can calculate its distance with incredible precision. Hubble patiently searched the great spiral nebula in Andromeda for these pulsating stars. And in 1923, he found one. The calculation he made from that one single star changed human history. He proved that the Andromeda Nebula was not a small cloud of gas inside our own galaxy. It was a colossal city of stars, a galaxy as large as our own, located at a then unimaginable distance of over 2 million light-years away. The universe was not a single island. It was an archipelago of countless and perhaps even infinite other islands. And with this new and powerful tool for measuring cosmic distances, Hubble was now ready to solve the great mystery of Slipher's redshifts. He began to painstakingly measure the distances to all of the galaxies that Slipher had measured the speeds of. And in 1929, he put the two sets of data together on a simple graph. On one axis was a galaxy's distance. On the other was its speed of recession. And the result was one of the most beautiful and most important revelations in the history of science. The data points formed a perfect and an unmistakable straight line. The farther away a galaxy was, the faster it was moving away from us. This was the first, direct and irrefutable proof that the universe itself is expanding. The discovery made by Edwin Hubble in 1929 was a true and a profound revolution, a moment that completely and forever altered our human perception of the cosmos. The old, comforting, and static universe of Einstein and of Newton was gone, and in its place was a new, a dynamic, and an evolving universe. A universe that had a history, a universe that was expanding. And the proof was there in the simple and the beautiful, and the undeniable straight line that appeared when Hubble plotted a galaxy's distance against its speed. This simple straight line is a depiction of a law of nature, what we now call the Hubble-Lemaitre law. And the most important property of this line, the single number that describes its precise steepness, has become the most important and now the most controversial number in all of cosmology. It is a number known as the Hubble constant. To understand the great mystery of the Hubble tension, we must first, with a quiet and a patient sense of calm, come to understand what this one single number truly represents. The Hubble constant, which is represented by the symbol h0, is a measure of the expansion rate of our universe. But its units can, at first, seem a little strange and confusing. The value is given in kilometers per second per megaparsec. Let us gently break this down. The first part, kilometers per second, is a familiar measure of speed. But the second part, the megaparsec, is a unit of truly cosmic distance. A single parsec is the distance that light travels in about 3.26 years. And a megaparsec is 1 million of these. So a single megaparsec is a distance of about 3.26 million light-years. It is a distance so vast that the light from a galaxy 1 megaparsec away has been traveling for more than 3 million years to reach our telescopes. So what the Hubble constant is telling us is the relationship between a galaxy's distance and its speed. It means that for every additional megaparsec of distance a galaxy is away from us, it appears to be moving away from us at an additional speed of a certain number of kilometers per second. This is the heart of Hubble's discovery. The farther away a galaxy is, the faster it is receding. To make this beautiful and strange idea feel more intuitive, let us use the most famous and the most gentle of all cosmological analogies, the raisin bread analogy. Imagine you have a large unbaked loaf of raisin bread dough. The raisins, scattered throughout the dough, represent the galaxies, and you, as an observer, are living on one single specific raisin inside this loaf. Now you place the loaf in the oven, and the dough begins to expand. As the dough itself expands, it carries all the raisins along with it. From your perspective on your home raisin, what do you see? You see that every other raisin in the loaf is moving away from you. But they are not all moving away at the same speed. A nearby raisin, one that was just 1 inch away from you before the baking began, might now be 2 inches away. It has moved 1 inch in that time. But a more distant raisin, one that was 3 inches away from you to begin with, might now be 6 inches away. It has moved 3 inches in that same amount of time. The farther away a raisin is, the faster it appears to be moving away from you. This is because there is more expanding dough, more expanding space-time between you and it. This is a perfect and a beautiful illustration of our expanding universe. The galaxies are not like pieces of shrapnel, flying outwards through a pre-existing empty space from a single central explosion. Instead, the very fabric of space-time itself is stretching, and it is this stretching that is carrying the galaxies, which are relatively still within their own local patches of space, away from each other. And this analogy also reveals another profound truth. From your home raisin, it looks as though you are at the very center of the expansion, as all the other raisins are moving away from you. But if you were to magically transport yourself to any other raisin in the loaf, the view would be exactly the same. From any raisin, it looks as though all the others are moving away. The expansion has no center, and so it is with our universe. We are not in a special or a privileged central position. An observer in any galaxy, anywhere in the cosmos, would see the very same thing. A universe of galaxies, all receding from them, with a speed that is proportional to their distance. The Hubble constant, then, is the single number that describes the rate at which this cosmic dough is rising. And it is, therefore, the single most important number in all of cosmology. For if you know how fast the universe is expanding today, you can run the movie backwards in your mind. And you can calculate when everything must have been in the same place. The Hubble constant, in a very real sense, tells us the age of our universe. For nearly a century, the great quest of observational cosmology has been the quest to measure this one single number with an ever-increasing precision. And it is this quiet and this patient and this noble quest that has in our own time led us to a place of the most profound and the most beautiful of all cosmic crises. To understand the great cosmic disagreement known as the Hubble Tension, our journey must now split into two separate paths. We must become two different kinds of detectives, using two completely independent methods to try and solve the same single mystery. Our first path is a journey backwards in time, a quiet and a patient exploration that will take us all the way back to the very dawn of our universe, to the oldest and the most ancient light that we can possibly see. We will, in essence, try to measure the universe's expansion by studying a photograph of its own beautiful and brilliant infancy. Let us now return, in our minds, to the story of the Big Bang. For the first brief period of its life, for about 380,000 years, the universe was an almost unimaginably hot and dense and in completely opaque place. It was a perfect and a uniform and a brilliant fog of plasma, a seething soup of fundamental particles and of pure energy, so hot that the simple, stable atoms that we know today could not yet form. In this primordial fog, the particles of light, the photons, were trapped. They could not travel more than a few inches without being scattered or absorbed by a free-floating electron. The entire universe was like the inside of a star, a place of brilliant light, but a place from which no light could escape. But as the universe continued its relentless expansion, it also continued to cool. And at the age of 380,000 years, it finally reached a critical and a truly magical temperature threshold, about 3,000 degrees Kelvin. At this temperature, for the very first time, the universe was cool enough for the free-floating electrons to be captured by the free-floating atomic nuclei. The first stable and electrically neutral atoms of hydrogen and of helium were finally able to form. And this simple and this beautiful act of chemistry, happening all at once, everywhere in the cosmos, was the most transformative moment in the history of our universe. It is a moment known as recombination. And in this moment of recombination, the great cosmic fog was lifted. With the electrons now safely bound up inside of stable atoms, the photons of light, the particles that had been trapped for 380,000 years, were at last set free. The universe, in an instant, became transparent, and the light that was released in this great cosmic unveiling has been traveling unimpeded through the cosmos ever since, but silent and eternal, and an ever-fading echo of the moment of creation. This ancient and beautiful light is what we now call the cosmic microwave background, or the CMB. It is not today a brilliant and a hot white light. Over the 13.8 billion years of its long and patient journey to us, the continued expansion of the universe has stretched its waves, cooling it down from its initial fiery 3,000 degrees to a faint, a cold, and an invisible temperature of just 2.725 Kelvin, just a few, scant degrees above absolute zero. It is now a faint and a perfect and a pervasive bath of microwave radiation, a gentle and an almost perfectly uniform warmth that fills every single corner of the entire observable universe. It is the oldest, the most distant, and the most profound phonograph that we will ever be able to take of our own cosmos. And in the early 2010s, the European Space Agency's Planck satellite, an incredibly sensitive and a beautiful space telescope, gave us the most detailed and the most perfect picture of this ancient baby universe that has ever been created. It is a strange and a beautiful and an oval-shaped map of the entire sky, covered in a complex and a beautiful pattern of tiny and almost imperceptible splotches of red and of blue. These are not static or noise from the camera. They are real. They are the genuine and the incredibly faint temperature fluctuations in that primordial cosmic fog. The red spots are the regions that were just 1/100,000th of a degree hotter and slightly less dense than the average. And the blue spots were the regions that were just 1/100,000th of a degree cooler and slightly more dense. These tiny and almost insignificant variations in the fabric of the infinite universe are the most important features in the entire cosmos, for they are the seeds of everything that was to come. These tiny, slightly denser blue spots were the primordial gravitational seeds, the gentle cosmic cradles, where over the next 13.8 billion years, all of the matter in the universe would slowly gather to form the first stars, the first galaxies, and the great, and the beautiful, and the intricate filaments of the cosmic web. This baby picture of the universe is a scientific treasure. and it contains, encoded in its beautiful and its subtle patterns, all of the information we need to write the next and the most predictive chapter of our story. We have now, in our shared and quiet journey, traveled back to the very dawn of time. We have stood in the presence of the oldest light in the universe, the beautiful and the faint, and the ancient afterglow of the Big Bang, a ghostly microwave light that we call the cosmic microwave background. We have learned to read the subtle and beautiful patterns in this light, the tiny variations in temperature that were the primordial seeds of all the great galaxies and structures that we see in the universe today. This beautiful baby picture of the cosmos is the first and the most crucial piece of evidence in our great detective story. But a single photograph of a newborn on its own cannot tell you how tall that baby will be when it is an adult. To make that kind of prediction, you need more than just a picture. You need a deep and a fundamental understanding of the rules of growth. In the world of cosmology, this rulebook, this great and beautiful recipe for how to grow a universe, is known as the Standard Model of Cosmology, or the Lambda CDM model. This is the great and the incredibly successful story that science now tells about the nature of our universe. It is our best and most complete recipe for the cosmos, a recipe that has been tested and confirmed by a vast and an overwhelming amount of observational evidence. And like any good recipe, it consists of two simple things: a list of ingredients and a set of instructions. Let us first, with a quiet and a patient sense of wonder, look at the list of ingredients that make up our entire universe according to this standard model. The first, and the most familiar of these ingredients, is what we call normal or baryonic matter. This is the good old-fashioned tangible stuff. It is all the atoms that make up the stars, the planets, the great glowing nebulae, the air we breathe, and our own bodies. This is the substance of our entire lived experience. And the first great and humbling surprise of our cosmic recipe is that this familiar matter, all of it, makes up only about 5% of the total substance of the universe. It is not the main ingredient. It is, in a sense, just the beautiful and the precious, and the almost insignificant garnish on the great cosmic dish. The second and the most substantial of all the ingredients is a mysterious and an invisible and a quiet substance known as cold dark matter, the CDM in our model's name. We cannot see it. We cannot touch it. It does not interact with light in any way, and yet we know it is there, because we can feel its immense gravitational pull. Dark matter, we now believe, makes up about 27% of the universe, and its role in the cosmic story is a crucial one. It is the great, invisible, and silent scaffolding of the cosmos. It is the dark, invisible flour in the cosmic recipe that provides all the substance and the structure. It was the immense gravity of this dark matter that acted as the great gravitational seeds in the early universe, the cradles in which all the normal, luminous matter could gather to form the galaxies. Without dark matter, our universe would be a thin and a formless and a mostly empty soup of hydrogen gas. And the third, the final, and by far the most dominant and the most mysterious of all the ingredients is a force known as dark energy, which is represented by the Greek letter lambda. Dark energy is the energy of empty space itself. It is a gentle, a pervasive, and a repulsive force, a kind of cosmic anti-gravity that is causing the very fabric of space-time to stretch and to expand at an ever-accelerating rate. It makes up the remaining, colossal 68% of the universe. In our raisin bread analogy, dark energy is the invisible and the mysterious and the powerful yeast that is causing the cosmic loaf to rise and to rise faster and faster over time. These three ingredients, a tiny pinch of normal matter, a healthy dose of dark matter, and a great, overwhelming measure of dark energy are the complete list of what our universe is made of. And the instructions for how to bake them are the fundamental laws of physics, most importantly, Albert Einstein's theory of general relativity, which tells us how these ingredients will interact with gravity and with the expanding fabric of space-time over the course of 13.8 billion years. This is our standard model, and its power is that it is an incredibly predictive one. If you take the beautiful baby picture of the universe that the Planck satellite has given us, with its specific pattern of hot and cold spots, and you plug it into this lambda CDM recipe, and then you let the simulation run forward in time for 13.8 billion years, the universe that it produces, the great cosmic web of galaxies and voids, looks almost exactly like the universe that we see around us today. The story works, and because it works so well, we can now use it to make a single and a very, very precise prediction. We can now ask our model the great question: based on this perfect baby picture and this perfect recipe, how fast should our universe be expanding today? We have now assembled the two great and powerful tools that are needed to perform our first great act of cosmic prediction. We have the beautiful and incredibly detailed baby picture of our universe, the map of the cosmic microwave background as captured by the Planck satellite. And we have the great and successful cosmic rulebook, the standard model of cosmology, our lambda CDM recipe that tells us the ingredients and the instructions for how our universe grows. The time has now come to put these two things together. We are about to use our knowledge of the universe's distant past to make a precise and a powerful prediction about its immediate present. We are about to calculate how fast our universe should be expanding today. The key to this entire process, the secret that is hidden in plain sight within the beautiful modeled pattern of the cosmic microwave background, is the size of the splotches. Those tiny, almost imperceptible variations in temperature, those patches of slightly hotter red and slightly cooler blue, are not random. They are, in a very real sense, the frozen echoes of sound waves that were rippling through the hot, dense plasma of the infant universe. In the first 380,000 years of its life, the universe was a battleground between two great opposing forces. The immense inward pull of gravity, primarily from the dark matter, was trying to pull the plasma into ever denser clumps. But at the same time, the immense outward push of the light, the radiation pressure of the photons, was fighting against this collapse, trying to push the plasma back apart. This great push and pull, this cosmic tug-of-war, created vast and slow and powerful oscillations in the primordial soup. It created, in a very literal sense, sound waves. The entire infant universe was ringing, like a great cosmic bell, with a deep and a silent and a fundamental note. And the beautiful splotches that we see in the baby picture from the Planck satellite are a direct photograph of these sound waves. Frozen in time at the very moment the universe became transparent. And this gives us an almost miraculous gift, because we know the ingredients of the universe with such incredible precision from our standard model. We can calculate exactly how far a sound wave could have traveled in that first 380,000-year period. This gives us a number, a physical distance. It gives us, in a sense, a standard ruler, a cosmic yardstick of a known and a definite length that has been imprinted directly onto the fabric of the infant universe. We know, with an almost unbelievable precision, the true physical size of the largest of those hot and cold spots in the baby picture. And now, the final, beautiful act of prediction can take place. We have a standard ruler from the dawn of time, and we can see, in our modern sky, the apparent angular size of these same patterns. So the process becomes a simple and a beautiful piece of cosmic geometry. If you know the true physical size of a distant object, and you can measure its apparent size in your sky, you can calculate, with an incredible precision, how far away that object is from you, and therefore, how much the universe must have expanded between then and now. The standard model of cosmology is the great and powerful engine that allows us to perform this calculation. We feed it the data from the Planck satellite, the precise map of our infant universe, and we ask it a simple question. Given these initial conditions, and given our recipe of dark matter and dark energy, and given the 13.8 billion years that have passed, how fast must the universe be expanding today for our picture of the past to evolve into the picture of the present that we see around us? The model runs its calculations. It evolves the universe forward, second by second, and year by year, through the long and the dark and the patient eons. And it gives us an answer. It gives us a single, a beautiful and an incredibly precise number. The verdict from the early universe, the prediction that is born from the beautiful and the ancient light of the cosmic microwave background, is that the Hubble constant should be approximately 67.4 kilometers per second per megaparsec. And the scientists who performed this calculation are incredibly confident in this number. The error bars, the small range of uncertainty around this value, are now incredibly and beautifully small. When Planck's first results were released in 2013, it felt like a triumph. Later, the 2018 legacy analysis refined those measurements and delivered the now famous prediction, roughly 67.4 kilometers per second per megaparsec. With beautifully small uncertainties, our first great cosmic detective, the one who has traveled back to the dawn of time, has now returned. And they have returned with a clear, a confident, and a very precise answer. The universe, they tell us, should be expanding at a rate of 67. And now, our detective story is only half over. For we must now send out our second detective, the one who will measure the expansion, not by looking at the past, but by looking directly at the present. Our first great cosmic detective has now returned from their long and quiet journey into the past. They have brought back with them a beautiful, a precise, and a powerful prediction, born from the ancient light of the cosmic microwave background and the elegant, successful mathematics of our standard model of cosmology. The message from the infant universe is clear. It tells us that our cosmos, today, should be expanding at a rate of about 67 kilometers per second per megaparsec. And so, the first half of our investigation is complete. Now, we must begin the second. It is time to send out our second detective. This one will not travel into the past. Their work is here and now, in the modern and the local and the fully grown universe. Their task is not to predict, but to measure. They will attempt, with a direct and an observational honesty, to determine the true and the real expansion rate of our cosmos as it is happening today. To do this, our second detective must measure two simple things for a large and a representative sample of our nearby galaxies. The first is their speed, and this, as we have learned, is a relatively easy task. An astronomer can simply look at the light from a distant galaxy, measure its redshift, and from that can calculate with an incredible precision the speed at which it is receding from us. The second task, however, is one of the most difficult, the most challenging, and the most noble quests in all of the history of astronomy. Our detective must measure a galaxy's true distance. To measure the distance to an object that is millions of light years away is a task of almost unimaginable difficulty. You cannot bounce a radar signal off of it. You cannot fly there with a long cosmic measuring tape. To solve this great and profound problem, Astronomers, over the course of more than a century, have built a beautiful, an ingenious, and a step-by-step method for measuring the universe. It is a method known as the cosmic distance ladder. The idea of the distance ladder is a simple and a beautiful one. You cannot measure the distance to a faraway mountain with a single giant ruler. So instead, you begin by measuring the distance to a nearby tree with great precision. Then you use your knowledge of the tree's size and position to help you measure the distance to a faraway hill. And then you use your new knowledge of the hill's distance to help you measure the distance to the even more distant mountain. You build up your knowledge step by step, rung by rung, with each new and more distant measurement relying on the accuracy of the one that came before it. The first, the foundational, and the most important rung on our cosmic distance ladder is a method of pure and of beautiful geometry. It is a technique known as parallax. You can experience this principle right now. Hold your thumb out at arm's length and close one of your eyes. Now, without moving your thumb, switch your eyes, closing the first and opening the second. You will see that your thumb appears to jump or to shift its position. Relative to the more distant objects in the background, this apparent shift is parallax, and the amount of the shift depends on the distance to your thumb. A closer thumb will jump more. A farther thumb will jump less. Astronomers do exactly the same thing, but on a much grander and more majestic scale. They use the orbit of the Earth itself as their two eyes. They will take a photograph of a relatively nearby star, and then they will wait for 6 months for the Earth to travel to the opposite side of its orbit, a distance of some 186 million miles. And from this new vantage point, they will take another photograph of the very same star, and they will see that the star has appeared to shift ever so slightly against the background of much more distant and seemingly fixed stars. By measuring the tiny and almost imperceptible angle of this shift, and by knowing the precise diameter of the Earth's orbit, they can use simple trigonometry to calculate a direct, a precise, and an almost completely unarguable distance to that star. This is our gold standard. It is our most reliable and our most honest cosmic ruler. But this beautiful geometric method has its limits. For stars that are very far away, the parallax shift becomes too small to measure, and so we must use our first and most reliable rung to help us build our second. We now use our parallax measurements to find the precise distance to a special and magical kind of star in our own local galactic neighborhood. We look for the pulsating stars that we have met before, the Cepheid variables. By using parallax to determine the true distance to these nearby Cepheids, we can precisely and perfectly calibrate the relationship between the speed of their pulse and their true intrinsic brightness. We are, in a sense, using the honest, geometric ruler of parallax to write the final and most precise instruction manual for our new and much longer cosmic measuring tape. Once this calibration is complete, we now have a tool that we can use to measure the distance not just to stars in our own galaxy, but to galaxies that are millions of light years away. Our cosmic detective, the one who is tasked with measuring the expansion of the modern universe, is now equipped with their first and most foundational tool. Through the beautiful geometric precision of parallax, they have built and have calibrated the next crucial rung on the cosmic distance ladder. They now have a reliable and a tested instruction manual for the wonderful pulsating stars known as Cepheid variables. They know that by simply watching how fast one of these stars is pulsing, they can know with a quiet and a beautiful confidence its true and intrinsic brightness. And so, The great and patient work of measuring the nearby universe can now begin in earnest. The process is one of almost unimaginable patience. An astronomer, using a great and powerful instrument like the Hubble Space Telescope, will point the telescope at one of our neighboring galaxies, a great, spiral-shaped city of stars, perhaps the beautiful Andromeda Galaxy, or the smaller and more delicate Triangulum Galaxy. And then they will wait. They will take a series of long-exposure images of that galaxy, not just once, but over and over again for many days, and many weeks, and many months, and then the true and patient work begins. In these vast and crowded images, containing hundreds of billions of individual stars, they will search for the handful of stars that are not steady. They will search for the tiny, almost imperceptible points of light that are rhythmically and patiently blinking, growing brighter and then dimmer and then brighter again, with a perfect and a clockwork regularity. Once a Cepheid has been found, the beautiful and simple logic of our distance ladder unfolds. The astronomer first measures its period, the time it takes to complete one full pulse from its brightest point to its dimmest and back again. Let us say it is 30 days. From the period-luminosity relationship, the instruction manual that was so carefully calibrated using parallax, the astronomer now knows the true absolute brightness of that star. They know exactly how much light it is truly emitting. They then measure the star's apparent brightness, how dim it appears in their telescope's image. And the final step is a simple and an elegant one. The difference between how bright the star is and how bright it appears is a direct and an unambiguous measure of its distance. It is the same intuitive logic that tells us that a distant headlight on a dark road is dimmer than one that is close by. Through this patient and meticulous work over a period of decades, astronomers have used Cepheid variables to build a beautiful and a reliable map of our local cosmic neighborhood, measuring the distances to dozens of our nearest galactic neighbors with an incredible precision. But this beautiful and powerful tool also has its limits. Cepheid variables, as bright as they are still just single, individual stars. And at a certain great distance, somewhere beyond 100 million light-years, even our most powerful telescopes, like the Hubble and the James Webb, can no longer distinguish these individual, pulsating stars from the great blended glow of their host galaxy. To measure the true large-scale expansion of the entire universe, we need to be able to see much, much farther. We need a final and an even more powerful rung on our ladder. We need a standard candle that is not just a single bright star, but an object so impossibly and so brilliantly luminous that it can be seen from clear across the observable universe. And the universe, in its deep and its beautiful wisdom, has provided us with just such an object. This is the final and the most powerful tool in our detective's toolkit. It is the spectacular and the violent and the astonishingly reliable death of a star. It is a Type 1a supernova. A Type 1a supernova is a very specific and a very special kind of stellar explosion. It begins its life as a binary star system, a two-star family, in which one of the stars is a small, a dense, and an ancient white dwarf, the stellar corpse that we have met before. If these two stars are in a close enough orbit, the immense gravity of the white dwarf can begin to pull or to siphon the outer gassy layers of hydrogen from its larger and more normal companion star. For millions of years, the white dwarf patiently and quietly feeds on its partner, pulling a steady stream of new material onto its own surface. And as it does so, it grows more and more and more massive. But this growth cannot continue forever. A white dwarf, as we know, is supported by the strange quantum mechanical force of electron degeneracy pressure. And there is an absolute and an ironclad limit to how much mass this pressure can support. That limit, known as the Chandrasekhar limit, is precisely 1.44 times the mass of our own Sun. And as the white dwarf approaches this critical and this fatal weight, the pressure and the temperature in its core skyrocket, and a new and a final and a runaway thermonuclear reaction begins. The entire carbon-rich star ignites all at once in a colossal and a truly cosmic scale explosion. And here is the beautiful and the miraculous key to their power. Because every single Type 1a supernova is triggered at this exact and this precise critical mass, the explosion is always and everywhere the same. They are, in a very real sense, standard bombs. The amount of energy they release, and therefore their peak intrinsic brightness, is incredibly and wonderfully consistent. They are all, in essence, perfect 100-watt light bulbs. And if you have a perfect, standard light bulb, you can use it to measure distances across the entire universe. For if you see one that appears dimmer than another, you know with a quiet and a beautiful confidence that it is simply because it is farther away. We have now, in our patient and step-by-step journey, assembled the final and most powerful of all our cosmic tools. We have climbed from the sure and steady geometric foundation of parallax up to the rhythmic and reliable, pulsating light of the Cepheid variable stars. And now we have arrived at the final and the most brilliant rung on our great cosmic distance ladder. We have found our ultimate standard candle, the beautiful, the violent, and the astonishingly consistent explosion of a Type 1a supernova. Because every one of these stellar cataclysms is triggered at the exact same critical mass, they all, in a very real sense, shine with the same intrinsic brightness. They are the great cosmic lighthouses, and their brilliant, brief, and beautiful light can be seen from clear across the observable universe. But before we can use this powerful new tool to measure the deepest reaches of the cosmos, we must first perform one final and crucial act of calibration. We must connect this new, final rung of our ladder to the one that came before it. To do this, astronomers must engage in a kind of cosmic waiting game, a patient and a hopeful search for a very specific and a very rare kind of cosmic coincidence. They must find a galaxy that is close enough to us that we can clearly see its individual Cepheid variable stars, and which has, in our own modern history, also been the host to a Type 1a supernova explosion. This is a rare but a beautiful alignment, and when it happens, it is a moment of profound scientific opportunity. For in these few precious Rosetta Stone galaxies, we can use our two great standard candles in perfect and beautiful harmony. The process is a simple and an elegant one. First, the astronomers use the tried and the true and the well-understood method of the Cepheid variables to calculate a precise and a reliable distance to that galaxy. Then, because they now know the true distance to the galaxy, and they can see the apparent brightness of the supernova that exploded within it, they can work backwards and can calculate the supernova's true intrinsic brightness with an almost unbelievable and a completely independent level of precision. By patiently observing dozens of these rare, coincidental events over many years, astronomers have been able to build a perfect and an exquisitely calibrated instruction manual for our new and most powerful cosmic ruler. The final rung of our ladder is now firmly and securely in place. And so, the great and patient work of our second cosmic detective, the one who is tasked with measuring the modern universe, can finally be completed. The great modern sky surveys with their powerful robotic telescopes patiently scan the heavens night after night, taking millions of digital photographs of hundreds of thousands of distant galaxies. Their powerful computers then sift through this immense river of data, looking for the telltale sign of a new and a sudden and a brilliant point of light, a star that was not there the night before. They are hunting for the fleeting and the beautiful and the incredibly rare momentary flash of a Type 1a supernova in a galaxy that is hundreds of millions or even over 10 billion light years away. When a new candidate is found, a great and a global alert is sounded, and the most powerful telescopes on and above our world are all turned to stare at this one single, spectacular event before its precious light fades away. For each of these distant stellar explosions, our detective now measures two simple things. First, they measure its light curve, the way its brightness rises and then fades over a period of weeks. From this, they can determine its peak, apparent brightness, and by comparing that to its known true brightness, they can calculate its distance. Second, they take a spectrum of the light from the supernova's host galaxy, and from the redshift of that light, they can calculate with an incredible precision the speed at which that galaxy is receding from us. And now, we have arrived at the final and the most beautiful moment of our second investigation. Our detective has now collected a vast and a beautiful catalog of data, a list of dozens and now hundreds of distant galaxies, and for each one, they have a precise measurement of its distance and a precise measurement of its speed. And just as Edwin Hubble did almost a century ago, they can now plot these two sets of numbers on a simple graph. On one axis is distance, on the other is speed, and the result is a modern, a beautiful, and an incredibly precise version of Hubble's original revolutionary discovery. The data points form a perfect and an unmistakable straight line. And the slope of this line, its precise and measured steepness, gives us the answer we have been searching for. It gives us a direct, an observational, and a completely independent measurement of the Hubble constant, a value that is born not from a prediction about the past, but from a direct measurement of the present. This great and patient work has been the life's mission of many astronomers, most famously the Nobel laureate Adam Rees and his SHIES team, which stands for supernova H0 for the equation of state of dark energy, originally aimed to study dark energy, though now focused on H0, and their most precise and their most confident measurement, a number that has now been cross-checked by multiple independent teams using slightly different methods, is a clear and an unambiguous one. The verdict from the modern local universe is that the Hubble constant is approximately 73.2 kilometers per second per megaparsec. And here at last, we have arrived at the quiet and the beautiful and the profoundly unsettling heart of our great cosmic mystery. Our two detectives have returned, and they have given us two different answers. The first, the one who traveled to the dawn of time, who studied the ancient light of the cosmic microwave background and used our perfect standard model of cosmology to make a prediction, has told us that the universe should be expanding at a rate of 67. And the second, the one who has patiently and meticulously built a great cosmic ladder to measure the modern universe directly, has told us that the universe is expanding at a rate of 73. The difference is not a large one. It is a quiet and a subtle and a seemingly insignificant 9%. But in the world of precision cosmology, a difference of this magnitude and of this statistical certainty is not a small discrepancy. It is a crisis. The tension is real. The universe of the past and the universe of the present are not telling us the same story. We stand now at the quiet and beautiful heart of our great cosmic mystery. Our two detectives, sent on two completely independent quests to discover the true expansion rate of our universe, have returned, and they have brought back with them two different and seemingly irreconcilable answers. The first, our detective who journeyed back to the dawn of time, who studied the beautiful and ancient baby picture of our universe in the cosmic microwave background, has returned with a clear and a confident prediction. They tell us that the universe, based on its initial conditions and our perfect standard model of cosmology, should be expanding today at a rate of approximately 67.4 kilometers per second per megaparsec. The second detective, the one who patiently and meticulously built the great cosmic distance ladder and measured the speeds and distances of the galaxies in our own modern universe, has returned with a different and an equally confident answer. They tell us that the universe, based on direct observation, is expanding at a rate of approximately 73.2 kilometers per second per megaparsec. To our human ears, this may not sound like a crisis. The difference is a subtle one, a quiet disagreement of only about 9%. It is tempting to dismiss it as a small and an insignificant rounding error, a minor detail to be ironed out by future, more precise measurements. But in the quiet and the meticulous world of precision cosmology, this small and gentle disagreement is the single most profound and most exciting challenge in all of science. This is the Hubble tension. And the reason it is a true tension and even a crisis is not because of the difference in the numbers themselves, but because of the incredible and the unwavering confidence that we have in both of them. To understand this, we must understand the quiet and the beautiful concept of the error bar. Every single measurement that is ever made in science, no matter how precise, has a small and an unavoidable range of uncertainty around it. This is the error bar. It is a quiet and a humble acknowledgement that our knowledge is never perfect. In the early days of cosmology, in the time of Edwin Hubble himself, the measurements of the expansion rate were incredibly difficult, and the error bars were colossal. His first estimates were in the hundreds of kilometers per second per megaparsec, numbers we now know were wildly incorrect. But over the last century, as our telescopes have become more powerful and our techniques more refined, these error bars have been shrinking and shrinking and shrinking. In the early 2000s, the error bars on the two different measurements of the Hubble constant were still large enough that they overlapped. This meant that the true value could, in theory, lie somewhere in that overlapping region, and that the disagreement between the two methods could still be explained by simple statistical uncertainty. But in the last decade, with the breathtakingly precise data from the Planck satellite for the early universe, and the equally precise and patient work of the Hubble and the Webb telescopes for the late universe, those error bars have now shrunk so much that they no longer overlap at all. They are two distinct and completely separate islands of certainty, with a great and an undeniable gulf of empty space between them. Scientists have a language for describing their confidence in a result, a statistical measure known as sigma. A 3 sigma result is usually considered to be good evidence, but the gold standard in particle physics, the level of certainty traditionally required to announce a true and a revolutionary discovery, is 5 sigma. A 5 sigma result means that there is only about a 1 in 3.5 million chance that what you are seeing is a random, statistical fluke. The disagreement between our two measurements of the Hubble constant has now reached this gold standard of 5 sigma. The universe is telling us, with a quiet, a calm, and a near absolute statistical certainty, that the disagreement is real. The tension is not an illusion. Let us think of it with another simple analogy. Imagine we have two perfect and independent biographies of the very same person. The first biography is written by studying the person's genetic code, their family history, and their childhood environment. From this incredibly detailed information, the biographer makes a very precise prediction of how tall the person should be as a fully grown adult. The second biography is written by simply going and measuring the height of the adult person, here and now, with a very precise and a very reliable ruler. The Hubble tension is the profound and the deeply unsettling situation where the predicted height and the measured height do not match, and it can only mean one thing. There is a deep and a fundamental and a previously unknown chapter in that person's life story, in their process of growth, that our first and otherwise perfect biography has completely failed to account for. Our story is missing a chapter. And so, the great detective story must now turn to a new and a final question. Is it possible that one of our two brilliant detectives has, in some subtle and quiet way, simply made a mistake? We are now standing in the quiet and the beautiful and the profoundly unsettling space between two different and competing stories of our universe. We have a story of the past, and we have a story of the present. And these two great and powerful narratives do not agree. The great cosmic biography that is written in the ancient light of the cosmic microwave background predicts a calm and a stately expansion of 67. The direct and the observational measurement of our modern local universe, a story that is written in the pulsating light of Cepheid stars and the brilliant, fiery explosions of supernovae, tells us a story of a much faster and a more energetic expansion of 73. The disagreement is real, the tension is undeniable, and so our great cosmic detective story must now turn to its next and its most important and its most humble of all possible chapters. We must now, with a quiet and a rigorous honesty, ask the most fundamental of all scientific questions. Have we simply made a mistake? Before a scientist can ever have the confidence to claim that they have discovered a crack in our fundamental understanding of the universe, they must first exhaust every single possible mundane explanation for their strange result. They must search with a tireless and a meticulous passion for a quiet and a hidden flaw in their own experiment, a subtle and an unacknowledged error in their own assumptions. This is the slow, the patient, and the often unglamorous but absolutely essential work of science. This is the search for a ghost in the machine. Let us first, then, turn a skeptical eye to our first detective, the one who has brought us the story of the early universe. Could the beautiful baby picture of the cosmos from the Planck satellite be wrong? The quiet and confident consensus is that this is incredibly unlikely. The data from the Planck mission is considered to be a gold standard of modern cosmology. It has been analyzed and reanalyzed and cross-checked by hundreds of independent scientists all over the world, and its results are found to be incredibly robust. The picture, it seems, is a true and an honest one. Could our understanding of the physics of that early time, the simple physics of the primordial plasma, be wrong? This, too, is considered to be very unlikely. This is a realm of physics that is very well understood, and which has been tested and confirmed in our own laboratories. And so, the prediction from the early universe seems to be a solid and an unshakable one. The number 67, it seems, is real, if our standard model of cosmology is correct. And so, the main focus of the search for errors has naturally fallen upon our second detective, the one who has measured the modern universe. For the great cosmic distance ladder, as beautiful and as ingenious as it is a complex and a multi-step process, and any chain is only as strong as its weakest link. Could there be a hidden, a subtle, and a systematic error in one of the rungs of our ladder that is throwing off the final result? Scientists have worked for decades to try and find such an error. They have questioned every single step of the process. Could our first and most foundational measurement, the geometric measurement of parallax, be wrong? This is almost impossible. It is pure and simple trigonometry. And in recent years, the European Space Agency's Gaia Space Telescope has been remeasuring the parallax of over 1 billion stars with an even greater precision. And this new and more precise data has only served to confirm the previous distances, and thus to sharpen the tension, not to resolve it. Could the problem then lie with our first great standard candle, the Cepheid variable stars? This has been a major area of focus. Perhaps our understanding of these beautiful, pulsating stars is incomplete. Is it possible that the light from other nearby stars is crowding our measurements, making the Cepheids appear slightly brighter than they truly are? This is a real concern, and it is one of the very reasons that the James Webb Space Telescope is now being used to reobserve these Cepheids. With its incredible and its sharp infrared vision, Webb can see through the dust and can more clearly separate the light of the Cepheids from their neighbors. And the initial results from Webb, so far, have seemed to confirm, with an even greater precision, the original measurements made by Hubble. Could it be that the Type 1a supernovae are not as standard as we believe them to be? We know that there are small variations between them, and astronomers have very clever and very sophisticated ways to correct for these. But perhaps there is some other, more subtle variation, one that is dependent on the age or the chemical composition of the host galaxy, that we have not yet accounted for. This is an active and an important area of research, and to address it, scientists are now developing entirely new and completely independent ways to measure the Hubble constant in the local universe, methods that do not rely on the Cepheid supernova ladder at all. They are using the light from gravitationally lensed quasars, or the gravitational waves from colliding neutron stars, as new and independent standard rulers. And while these new methods are still in their infancy, their early results have, so far, tended to lean closer to the higher and the faster value of 73. And so, the search for the simple mistake, for the single loose wire that could explain away the entire mystery, has so far come up empty. With every new observation, with every new cross-check, and with every new independent measurement, the Hubble tension has not gone away. It has, in fact, only become stronger, more persistent, and more statistically undeniable. The quiet and the reluctant, but the increasingly confident, conclusion that is now being reached by the world of observational cosmology is a simple one. Our detectives have not made a mistake. The two numbers are real. We have now, in our quiet and methodical investigation, arrived at a place of profound and of beautiful difficulty. The great and patient work of our cosmic detectives has been completed, and we are left with a single, an undeniable, and a deeply mysterious conclusion. The two most powerful and most trusted methods that we have for measuring the expansion rate of our universe are giving us two different and statistically irreconcilable answers. The search for a simple mistake, for a quiet and a hidden ghost in our own machines, has so far come up empty. And so the world of cosmology now finds itself in a state that is both deeply unsettling and incredibly exciting. It finds itself in a state of crisis. The word crisis in our everyday lives is a heavy and a frightening one. It is a word that we associate with moments of danger, of confusion, and of things falling apart. But in the quiet, the patient, and the ever-evolving world of science, a crisis is something very different. A true and a deep and a beautiful scientific crisis is not a sign that science is broken. It is, in fact, the most powerful and the most definitive sign that science is working perfectly. It is the thrilling and the hopeful and the long-awaited moment that a great and a beautiful and a long-held scientific story finally and gracefully meets the gentle and the immovable and the beautiful authority of a contradictory fact. Let us think of our scientific understanding of the universe as a great and a beautiful map. For the last 50 years, our standard model of cosmology, the lambda CDM model, has been the most perfect and the most detailed map of our reality that we have ever had. We have used this map to navigate the entire known cosmos from the moment of the Big Bang to the present day, and it has, in almost every single case, been a perfect and an unerring guide. But the Hubble tension, this stubborn and undeniable disagreement between the past and the present, is the quiet and the gentle and the unmistakable discovery that our beautiful map is, in some way, incomplete. We have, in our long and our patient explorations, finally and beautifully sailed off the edge of our known world. This is not the first time that this has happened in the history of science. The entire story of our understanding is a story of these beautiful and productive crises. For more than 2 centuries, Isaac Newton's law of universal gravitation was a perfect and a beautiful map of our solar system. But in the late 19th century, a tiny and a nagging and an inexplicable crisis emerged. The orbit of the planet Mercury, the innermost of all the planets, had a tiny and a strange and a persistent wobble that Newton's great and beautiful map could not quite explain. This small and seemingly insignificant crisis in the clockwork universe was the clue that eventually led Albert Einstein to his general theory of relativity, a completely new and a much deeper and a more profound map of gravity, a map that was written in the beautiful and the curved language of spacetime itself. In the early 20th century, the great and comfortable story of our universe was that it was a static and an eternal and an unchanging place. But the quiet and the patient and the inexplicable redshift measurements of Vesto Slipher and the brilliant and the revolutionary distance measurements of Edwin Hubble plunged that old and comfortable story into a crisis from which it would never recover. And from the beautiful ruins of that old and static idea, our entire modern story of an expanding universe and of a hot and a dense and a creative Big Bang was born. The Hubble tension is the next great and beautiful crisis in this long and noble lineage. Our standard model of cosmology is our new and our beautiful and our incredibly successful map. But the persistent and the undeniable disagreement between the expansion rate of the past and the expansion rate of the present is the new and the quiet and the beautiful wobble that our map cannot explain. It is a gentle and an insistent and a wonderful whisper from the universe itself, a whisper that is telling us that there is a deeper and a stranger and a more wonderful story that we have not yet learned how to read. A crisis in cosmology, then, is not a cause for anxiety. It is a cause for profound and for quiet celebration. It is the most exciting and the most hopeful and the most fertile moment in all of science. It is the moment that a great and a locked door, a door that we did not even know was there, has been found. And it is the moment that the entire global and collaborative community of science now gets to work together in a great and a patient and a creative quest to try and find the new key that will open it. And so we arrive at the quiet and the thrilling and the beautiful frontier of our knowledge. Our patient and our meticulous and our careful investigation has led us to a single and an almost inescapable conclusion. The Hubble tension is real. The disagreement between the past and the present, between the prediction and the measurement, is not the result of a simple mistake. It is a deep and a fundamental and a statistically significant feature of our universe. We have sailed in our shared and scientific journey to the very edge of our beautiful and our trusted and our successful map of the cosmos. And we have found, with a quiet and a beautiful certainty, that the map is incomplete. The crisis we must now accept is a real one. And so, we are now left with only one final and truly revolutionary possibility. The story must be missing a chapter. We must, in some way, change the cosmic recipe itself. We must now, with a sense of profound and of quiet excitement, explore the strange, the beautiful, and the wonderful new ideas that are being proposed for this new physics. The first, and perhaps the most elegant and popular, of these new ideas is a concept known as early dark energy. As we have learned, our standard model of cosmology assumes that the amount of dark energy, the mysterious force that is accelerating the expansion of our universe, has been a constant throughout all of cosmic time. But what if it was not? This new theory proposes that in the very first moments of the universe's life, in the hot, dense era before the cosmic microwave background was formed, there existed a new and a temporary and a more powerful kind of dark energy. This early dark energy would have given the infant universe an extra and a very powerful outward push, causing it to expand even faster than our standard model predicts. This initial, supercharged expansion would have a profound and a direct effect on our measurement of the Hubble constant from the early universe. It would mean that the sound waves rippling through the primordial plasma, the great cosmic yardstick that we have measured in the CMB, would have shrunk more rapidly than we thought. If our standard ruler is actually a different size than we have calculated, then our entire prediction for the Hubble constant must be revised. This brief and an ancient and a now vanished burst of early dark energy could be the one single missing ingredient in our cosmic recipe that could perfectly and beautifully resolve the tension, bringing the prediction from the early universe up into a harmonious agreement with the direct measurement of our modern local cosmos. A second and a related possibility is that the early universe contained not a new kind of energy, but a new kind of particle. Our standard model contains a well-known family of light and fast-moving and ghost-like particles, the neutrinos. But what if there is another, a new and a previously unknown species of relativistic particle that also filled the infant universe? This new ingredient is often referred to as dark radiation, a new and a sterile kind of neutrino, for example, or some other exotic and fast-moving particle that does not interact with light or with normal matter. The presence of this extra dark radiation would have also changed the cosmic recipe. It would have added more pressure to the primordial soup, altering the way that the sound waves traveled through it, and once again, changing the fundamental calibration of our standard ruler in the cosmic microwave background. Like early dark energy, this quiet and an unseen and a ghostly new particle could be the one simple and elegant addition to our story that makes the past and the present agree. A third and an even more profound possibility is that we have misunderstood the nature of the dark sector itself. Our standard model assumes that dark matter and dark energy are two completely separate and non-interacting entities. But what if they are connected? What if they can, in some slow and gentle way, talk to each other? This is the idea of an interacting dark sector. Perhaps over the long and the patient eons of cosmic time, the particles of dark matter can slowly and gently decay into dark energy. Or perhaps they can exchange energy in some other, more subtle way. If this were true, it would mean that the amount of dark energy in our universe is not a constant, but is a dynamic and an evolving thing. And this slow and an unseeable and a quiet conversation between the two great and mysterious dark components of our universe could be the missing chapter in our story, the secret and the hidden mechanism that can resolve the beautiful and the profound tension between what was and what is. These are just a few of the beautiful and the exciting new ideas that are now being explored by scientists. They were all, for now, purely speculative. They are all a testament to the incredible and the creative power of the human mind when it is faced with a beautiful and a profound mystery. The Hubble tension has not broken cosmology. It has, in fact, given it the greatest of all possible gifts. It has thrown the doors of our understanding wide open, and it has invited us to imagine a universe that is richer, that is stranger, and that is more wonderful than we had ever dreamed. Our long and quiet exploration has now brought us to the very frontier of modern cosmology. We have journeyed through the history of our understanding, from the first revolutionary discovery of an expanding universe to the beautiful and meticulous methods we now use to measure that expansion. We have seen how the two great and powerful stories of our cosmos, the story told by the ancient, infant universe and the story told by the modern, local universe, are in a state of quiet and profound disagreement, and we have, with a sense of gentle and of hopeful curiosity, explored the strange and the beautiful new physics that might one day resolve this great and beautiful crisis. And so, as our journey nears its final quiet conclusion, it is time for us to take one last step back and to reflect on what this all means. What is the ultimate and most peaceful message of the Hubble tension? The true and the most beautiful message of this cosmic crisis is not to be found in any one of the specific potential solutions. The true message is in the existence of the mystery itself. A scientific story that is complete, a map that has no unexplored territories, a puzzle that has been perfectly and finally solved, is also a story that is, in a sense, over. The Hubble tension is a profound and a beautiful and a welcome gift from the universe. It is a quiet and an insistent and a gentle reminder that the great cosmic story is far from finished. It is a guarantee that there are still deep and wonderful and revolutionary new discoveries waiting to be made. For the last few decades, our standard model of cosmology has been so incredibly successful that it was beginning to feel like the final chapter. The Hubble tension has joyfully and beautifully and completely torn out that final chapter, and has revealed to us that the book of the universe is far longer and far stranger and far more wonderful than we had ever dreamed. It has infused the entire field of cosmology with a new and a vibrant sense of excitement. It is a quiet and a thrilling time to be an astronomer. It is a time when our most fundamental and deeply held assumptions about the nature of reality are once again being questioned. It is a time when the next great and revolutionary and Einstein-level discovery could be waiting just around the corner. And in this beautiful and productive uncertainty, we can find a deep and a profound and a personal peace. The Hubble tension is a powerful lesson in the beauty of an unfinished story. It teaches us that the true spirit of science, and perhaps the true spirit of life itself, is not to be found in the comfort of a final and an absolute answer, but in the quiet and the patient and the ever-unfolding journey of the question. It is an invitation for us to let go of our need for certainty and to instead learn to rest with a sense of deep and of abiding wonder in the face of a great and a beautiful mystery. The Hubble tension is the universe in its quiet and its gentle way speaking to us. It is telling us that it is not obligated to conform to our most elegant equations or our most successful theories. It is telling us that it will always be more complex, more subtle, and more magnificent than our best and most beautiful stories about it. It is the latest chapter in our great and humbling demotion, a continuation of the journey that began when we first learned that the Earth was not the center of the universe, and that our galaxy was not the only one. And now, we are learning that our understanding of the universe itself is not the final one. This is not a loss of our importance. It is a quiet and a beautiful gain of our perspective. It is a final confirmation that we live in a universe that is still full of magic and of wonder and of beautiful and of yet to be answered questions. And to know that, to truly feel that, is to feel a sense of profound and of quiet and of hopeful peace. Our long and quiet exploration of the Hubble tension has now reached its peaceful conclusion. We have journeyed from the dawn of time to the modern day and have arrived at the shore of a great and a beautiful mystery. The story of our cosmos, we have learned, is still being written, its greatest secrets still waiting to be discovered. The tension between our past and our present is not a flaw in the universe, but a beautiful and a thrilling invitation to a deeper and a more wonderful understanding. The story is now told. The great cosmic tension will be there for the scientists to solve tomorrow. But for you, tonight, the only task that remains is to release the tensions of your own day. The journey is over, and now you can rest in the quiet and the peace of the great and still unfolding mystery. Let the great, silent, and expanding universe hold you now. There is only the quiet, only the calm, and the gentle invitation to drift off into a deep and a peaceful sleep. Rest now. Just rest. The journey continues, always calmly, always at the pace of the universe.